these occasions, there is a kind of laudation of the new member of the Academy. So that's supposed to be what I'm doing now. In 1996, in December, early December, late November, early December 1996, I got a letter from Jean-Christophe Jocoz, who at the time was the head of department of mathematics at Université Paris-Sud d'Orsay, asking me to write a reference for a young person who was applying for a professorship there at the time. Now, this young person is sitting here now, still young. And I wrote one. I was much honored to do this at the time. It was the beginning of our collaboration with Wendelin. So this is a 3 pages long reference written almost 30 years ago, which I'm not going to read now. I will read only one single sentence from there, which is a sort of after exposing his work and so on and so on. What I wrote here was 29 years ago was, informally speaking, there is a small group of young stars in probability theory, not necessarily related between themselves, but definitely identifiable as a new wave in probability theory. Wendelin Werner is among them for sure. So that was a kind of informal conclusion of the letter I wrote at the time. I think I could stop before doing that. So that was 1996. This was dated January 1997. And you know what happened about 9 years later. Needless to, okay, maybe not needless to say, so Wendelin got the Fields Medal. So I could stop my laudation right here, but this place and this institution is more conservative and conventional than letting me do that now, so better I do a little bit more formal thing. So Wendelin, so he is, in my view, a pan-European intellectual who happens to live in Cambridge right now, and he's a Rose Bowl professor of mathematics at the Department of Mathematics, of Pure Mathematics at the University of Cambridge. This club of Rose Bowl professors includes Littlewood, Besikovic, Davenport, Thomson, Hitchin, Gowers, and now Wendelin. So this is the club. I will not tell you all the details of his CV before you can read it in many places. He was trained as a stochastic analyst, and very, very early, as a PhD student already, he realized that the relevance of statistical physics in probability theory and mathematics. And what I think I formulated for myself in this way, that he not only belongs, but was one of the initiators of what I call a second revolution in probability theory in the late 20th century. The first one was in the 70s, late 60s, early 70s, when Dobrushin, Sinai, Lanford and others came up with the new formulation of statistical physics and caused a real revolution in probability. A second revolution was caused in the late 90s, started in the late 90s, which resulted in the understanding of phase transitions two-dimensional conformal invariance of phase transition in proper mathematical terms. He's best known, of course, for his work joint with Lawler and Schramm on stochastic Löwner evolution and conformal description of two-dimensional phase transitions. I don't have time to go into details here, but there are other very important contributions before and after the stochastic Löwner evolution story. Intersection and disconnection exponents of two-dimensional Brownian motions very early in his career, which became a very important thing. Construction of non-conventional processes, which also became an interesting stuff still before SLE, then past SLE, the Brownian loop story, Brownian loop substory, we will hear more about, conformal loop ensemble, and so on. So really important things. Now, speaking about recognitions, accolades, and distinctions, there are too many to list them all. He got I will tell you only two of the most important ones, namely the prize of the European Mathematical Society for Young Mathematician Prize of the European Mathematical Society in 2000, and as you know well, the selected member of various academies of sciences like Akademie des Sciences, Akademia Europaea, the Berlin-Brandenburg Akademie der Wissenschaften, Deutsche Akademie der Naturforscher Leopoldina, Royal Society of London, and add to this now the Hungarian Academy of Sciences. One more thing I want to add, and I'm sure Wendelin thinks about this as a most important achievement in his professional career, is the School of Probability, created by him partly in Paris, continued at ETH, and now in Cambridge. I will not name his academic offspring and academic grandchildren who are already there to do the third revolution in probability theory, possibly in the next decades. So I think, okay, one more personal word about all this. So for me personally, it was a privilege to have the occasion to collaborate with this young person, and that's all I wanted to say.
Thank you, and thank you very much for the setup and the very nice introduction. I understand that you can still, the pressure is a bit on me, because if the talk really goes badly, you can still decide to not hand over the diploma at the end, so I'll try to do my best not to disappoint you. One thing you realize as a scientist, especially as a mathematician, is that an academic life feels even shorter than life itself. And so I can hardly believe that it has been almost 30 years since I first came here and went to the Rainy Institute and discovered saw all these famous names of Hungarian probability school that were actually all there together in mainly the same nice room, and was a memorable experience. And of course, probability theory has a long tradition in Hungary, and I'm very much honored to be part of this institution now. Of course, you might argue that maybe I represent a part of probability that is sort of more focusing on where the discrete probability turns into something continuous. It's sort of this weird moment where you start with coin tosses and then you have these random continuous objects with very strange properties. And in some sense, I'm mostly reflecting. I can see that I'm mostly attracted by those objects where at that moment when you move from the Hungarian discrete type understanding of probability theory this jump into the continuum actually has some mysterious or surprising or unexpected features. That's maybe the story I want to slightly discuss with you a little bit. Another little remark I want to say, sort of just to say the general setup in which the story I'm going to tell you falls into, is that maybe historically, in its interaction with other fields, it's fair to say that very often, a very strong connection between probability theory and other parts, either of mathematics or with statistical physics, has been revealed, and which did enlighten a lot, the understanding of these other questions. On the other hand, the number of times at which probability theory was the first tool that enabled to understand these other areas or other questions that do not necessarily originate from probability theory were quite sparse. So, nowadays, if you're trained as a probabilist, you like to think that, solving the Dirichlet problem or the Cauchy equation has something intrinsically to do with Brownian motion, and it's, evolution of heat. But of course, in the 19th century, the people didn't wait for the invention of, proper introduction of Brownian motion in order to, solve the Cauchy equation or the heat equation. And similarly, Einstein used, Brownian motion as a tool to, compute the Avogadro number way before, it was actually made clear mathematically that Brownian motion was a mathematical object, a continuous trajectory, and so on. And of course, in all these cases, you could argue that probability theory arrived too late, right? Sort of like too late then. And then, of course, it goes all the way in quantum mechanics. That you look at Feynman's lecture on quantum mechanics. Basically, at some point, he says, forget it. Don't try to give a probabilistic cook up some probabilistic, incarnation and explanation of what is going on the microscopic world, the quantum world, because it doesn't work. Forget it. And so, in some sense, I might argue that probably that, might be worth still to try, to try to cook up some probabilistic, natural objects, study them, and maybe detect some things that are reminiscent of the stories we are not supposed to have understood before. And so the object I'm going to describe to you is something that, in some sense, interpolates nicely, is a way to approach the continuum limit by something that looks almost like something discrete, but has some hybrid features. So let me immediately start with sort of defining to you what this Brownian loop soup on cable systems is. So I'm a very old-styled mathematician. I like blackboards, and when no blackboards are available, I do all sorts of complicated tech operation in order to actually have a blackboard and use it as a blackboard, which is this screen here. So if you want to approximate the continuum, right, the usual way one goes about in statistical physics when you deal with percolation or discrete model from statistical physics is always to, you take a fine grid and you let the mesh size of the grid goes to 0. And, the randomness happens at the sites. Okay, that corresponds to each site is associated something random, a random variable that goes on at those sites. The object I'm going to discuss now lives actually on this sort of metric graph associated to these cable discrete objects. So we jump away from proper combinatorics, if you want, into the sort of semi-continuous world where basically, these edges now are physical edges. Okay? So cables, if you want. Okay? So of course, this is what you do when you do electric networks and so on, but that sort of here is going to be very, very important in what's going to follow. So when you have a cable graph like this, it is very easy to define, first of all, on it Brownian motion on the cable graph. Whoops. Which is simply explained this random particle that moves around, continuously on these edges, and each time you sort of arrive at the vertex, which has, say if you are in D dimension, 2D incoming edges, then sort of each time you go away from that vertex, you choose one of the 2D edges uniformly at random, and you try to escape in that direction, and then if you come back, then you start again. So it's just intuitively very clear what this object is. It's sort of, choosing at random a random continuous function that moves around on this graph. For what I'm going to tell you, in some sense, you don't really need time or it's just this random function that moves around in an isotropic way, if you want, on this cable graph. So you see that in this way, this d-dimensional world is both discretized, because it sort of looks, you don't have to deal with these d-dimensional structures. It's always locally one-dimensional, except at the vertices where you have still one-dimensional things that meet. But it's still already continuous, because you have this one-dimensional continuum that joins different points. So once you have Brownian motion, there's a very natural variant, which is Brownian loops. So now this is a random trajectory that moves on the cable graph, moves like, each time you reach a vertex, you try to escape from it in all directions, then you come here and so on. And then at the end, it's a loop. So you decide to start again from where you arrive where you started, and you do it like this. And intuitively, it is quite clear that if there's a natural measure on Brownian motions on the graph, maybe there is a natural measure on the set of Brownian loops that live in this graph, especially if you're on a graph which is transient, where a random walk goes to infinity, right? So if you start from the origin, you're going to come back a certain number of times to the origin, but eventually you're going to go away. So you can just look at the law of this first batch between where you start and the last time you come back. That's a loop, sort of a random loop. And you can be interested in that type of structure, and it will be a random Brownian loop. The important feature is that the random Brownian loops that I'm going to look at, or this measure on Brownian loops, is a measure that the objects you're looking at are loops, meaning they don't have any marked starting point, right? They are just closed curves that you define on your cable graph. And they are sort of, you could view this measure as sort of the spontaneous way in which you want to say, okay, a loop appears somewhere with that particular likelihood, which would be sort of given by this measure on Brownian loops on the cable graph. Now, as if you want to come from physics and things having to do with bosons or something like that, you can maybe do something like saying, one loop is a bit like a particle, right? It's just, a way to spread a mass in your graph in some localized way, all right? It's a way to say, this particle is somewhere spread on this trajectory in some way. That's something it's good to have in mind. Right. So if you look at this measure on Brownian loops, one very obvious thing that you end up noticing is that the mass of loops that live only on one edge, of very small loops. This measure, if you focus on one edge, you look at the measure focusing on the half edge and on the loops that stay inside this half edge. You want these two things to be the same, so that this measure should be self-similar on each edge. That's what this measure turns out to be, and therefore you have an infinite mass of small loops, on each edge, because at each scale you will have a certain mass of loops of scale 1, 1/2, 1/4, and if this thing is self-similar, you will end up having an infinite mass. Now, if you are a probabilist, what you do is you do this Brownian loop soup, which is this object we introduced with Greg Lawler first in the continuum two-dimensional world, because it turned out to be crucial there. So this is the Brownian loop soup, which is just doing it, you view this measure on loops as sort of the likelihood of appearance, of spontaneous appearance of such loops. And then we do what we call a Poisson point process of loops with that intensity, which means that everywhere at the same time, loops will try to appear with that likelihood given by that measure, and you wait until time 1, and what you see is a picture where now you have, a countable collection of loops that did appear on your cable graph. Okay. So the way I want you to think of this is you have your cable graph. On your cable graph, you have infinitely many loops that have appeared. On the other hand, there are infinitely many, but it's mostly due to the fact that you have infinitely many small ones. As it turns out, if you are in, say, the cable graph of Z3 or any other transient graph, then there will still be points, exceptional points on the cable graph that have been visited by no loops at all. All right? So the loops, there are infinitely many loops, but they sort of agglomerate in such a way that there will still be exceptional points on the graph that are not visited by any loop. So in particular, if you look at the, if you're colorblind and you look at the union of all the loops in a sample of this loop soups on the cable graph, you have different connected components because they will be separated by these points that are visited by no loop. So when you have these cloud of loops that fall down, then you look at the connected components of the union of the loops. And now I'm going to try to explain to you why that is a very natural thing to do, and why. Okay, so how do I going to go here? So it turns out that if you tune things correctly, this collection of loops has a very important property that I like to call the rewiring property, which means that imagine that you see one loop going this way here. So of course, it's closed over there. And then you see another loop, here, and they meet here at this point. As soon as two loops meet, you can do the following operation. You just look at what happens here, and you could try to resample. You have 4 incoming edges, 4 incoming trajectories coming in, and you can resample to decide, whether maybe, this connection goes this way, this connection goes that way, as is here, or this connection goes the third way, which is over here. And because the loops in my picture are not oriented, all these 3 would be admissible. That means if 2 meets, you could decide to merge them into one single loop. Or, in the same way, when one loop has a double point, you can resample the situation there, and then see that with probability 1/3, you will split it into 2 loops. So in some sense, if you do this resampling operation everywhere, the law of the, you're going to merge loops or split loops, but the law of the collection of loops that you look at will be preserved. And in some sense, it's almost, if you think about it, it's almost a characterization of this measure on Brownian loops, if you want, is sort of the fact that, it's this Poisson point process of loops that have the property that as soon as 2 loops meet, you could decide to merge them or to split loops into 2 pieces in such a way that is measure preserving. So in other words, that means the following, that as soon as 2 loops meet, if you're colorblind and you only see the union of the loops, you just don't know. You have no information about which of these 3 configurations you are playing with. Right? So in some sense, as soon as 2 particles, 2 loops meet, they become indistinguishable, and then suddenly you don't, you can treat them as one object, which is the connected component of these clusters of loops, because then the union of the loops is, that object is preserved, and the way one connected component is split into individual loops just corresponds to independent choices of that type at every double point in your picture. So this, what I sort of called resampling property or rewiring property, is in some sense reflecting some idea coming from physics as well. And it's not a surprise that this object that I'm talking about, this Brownian loop soup, is very directly connected in some almost bijective way in what physicists call the Gaussian free field or the bosonic free field in the textbook in statistical physics. And as you know, bosons are these indistinguishable particles which have this property of losing individual identities as soon as they meet, because they become indistinguishable. All right. So this loop soup has this sort of rewiring property, which is, in some sense, explaining, or can be a posteriori used in order to understand things have to do with, Markov property in space of these type of structures. All right. So this is this rewiring property, and so now what we are interested in, the structure we are interested in, are therefore these clusters of Brownian loops on the cable graph. So here is where somehow the continuous world is very important compared to the discrete world. You could, in the same way, describe random loops on a discrete graph. There are random walk loops that move on the discrete graph. You could do similar things with clusters of loops on the cable. You still have this rewiring property can also be made to work on the discrete world. On the other hand, the way I'm going to describe the clusters of Brownian loops and everything that comes now is really intrinsically related to the idea that I use the cable graph, because if I imagine I have a loop that went here, came here, went there, and then on the neighboring vertex I have another loop that, the yellow one here, that came down here and continued that way, they might not intersect. And therefore, the cluster, are they in the same cluster or not? Well, it depends on the structure of the loops that live just inside this little edge between them. So you might have little small vertices that don't go through, little small loops that live on the edge. They don't hit any, they can't be seen at any vertex because they don't hit any vertex. And they are the ones, that are gluing together these yellow and the red ones together into one single loop. And therefore, making these two loops into one single connected component and being indistinguishable. Right? So the idea is if 2 points belong to the same cluster of loops, then it means that it might be that actually they are part of the same loop, living in the same cluster, right? That's sort of one moral of the story. And for that, you need the knowledge about the little ones. So a first miracle, sort of a first, combinatorial feature that is very important in that model is that as opposed to all, this looks a little bit like a percolative model. Some things appear independently at random, in that case loops. And then you just look at, how big is the connected component of this union of loops. If you are in a dimension of space which is high, say greater than 7 or greater, then somehow, loops are pretty small. It's more difficult for a Brownian motion to come back at its starting point, so you will have fewer and fewer big loops, and then it will look more and more like actual percolation, where at big scale, the loops that you see in your graph will be just small objects that you try to agglomerate to construct large clusters. And as opposed to all these discrete models where basically there's no explicit formula for anything involving connective probability, when you are looking at clusters of loops on the cable graph, there's an explicit expression for the probability that 2 point x and y are in the same cluster of loops. So that's a formula that was first written down by Titus Lupu, which is explicit, and it's a very simple function in terms of the Green's function between x and y on the graph. So the Green's function is just starting from x, what the expected number of time you spend at y, if you are doing the Brownian motion until you go away. So in particular, what you already see here is that when x, if you are in ZD, and I take d greater or equal to 3 here, then this will be easily shown to be just behaving like the Green's function between these 2 points when x and y are very far away. So in particular, if you're in 3 dimensions, this is like the Newton potential, and you have the probability that x is connected to y will decay like 1 over the distance between these 2 points, and you have already isotropy, everything. Everything will be expressed in terms of probabilities having to do with the continuum Brownian motion, one-dimensional Brownian motion in the end. All right? And so this is already a signal that this model of loops has some features that A, related very natural to potential theory and Brownian motions itself, because you see that the Green's function comes up here, but also it's a model where you're able to say much more than critical population in ZD itself, where these type of questions about what is the decay rate of the probability in 3 dimensions that 2 points are connected to each other is a very hard nut, and it's believed to be, of course, something else than 1 over r, but it's a very difficult question. All right, so now I'm going to tell you 3 results, 3 ideas about this model of loops that I want to convey now. So idea 1, or result 1, okay, I didn't check it all the time. Okay. Result number 1 is, and that's always dangerous because that's a 2025 paper. And it's always easy to get too excited about the recent stuff and forget about that, to put things in perspective. But this is something that is easy to explain. So here, we have an explicit expression for the probability that x is connected to y. But then you may want to ask, what is, and it involves something that is reminiscent of Newtonian potential. And just as I'm not claiming anything about gravity or anything, but for me, the motivation thing, one of my driving things always has been, something saying, how does gravity work, right? How does the exchange of information between, masses, actually works in practice? And there's always this problem that, if something diffuses, if, some mass sends some information out, because it's transient, it diffuses, goes to infinity, and there's some sort of a dissipation of something which doesn't really work. And so when I saw this result, I said, aha, maybe that I like this because it's a sort of reminiscent of type of questions I was looking at for a long time. So here, the idea is the following. If you are in a configuration where 2 faraway points x and y are connected to each other, you condition on that what is the conditional distribution of your clusters, right? If you condition on this very exceptional moment where x and y are connected to each other by some chain of loops, how do the clusters look like? And I'm going to simplify slightly the result, so I'm cheating a bit, but only a little bit. And the result is the following, is that so conditioning on x being connected to y is the same, almost, as just adding one Brownian, what we call excursion, joining x and y to an otherwise unperturbed usual configuration. So what I have in mind here is, number one is just a collection of configuration, a configuration where you have this chain of loops on this any cable graph here, like this, which has the property that x and y are connected by a chain of loops. So it's a configuration where potentially x and y could be the same visited, they are the same boson somehow. They happen to be able to communicate via this chain of loops. Right? It's the moment where x and y suddenly say, oh, I can see you through this random chain of loops. So that is number one, is if you condition on that special event. And number two is the picture I'm going to draw on the right. It's just take a normal configuration where x will be in one cluster here, y will be in another cluster here, and then you have lots of clusters around. And to this configuration, you just add one random path independently of all the others, which is basically chosen according to the random Brownian trajectory that joins x and y. It's one trajectory, it's open-ended, it's not a loop anymore. It's just one trajectory, and it's what I call an excursion, meaning and the way this one is distributed is exactly, you start the Brownian motion started from x, you wait until you hit y, if it happens, and that will happen with this probability 1 over r, by the way, which is just this, of order Green's function. And then you just keep the part of the trajectory between the last time you visited x and the first time you visited y. It's sort of an excursion. It's a path from joining x to y that does not revisit x, or does visit both x and y only once at the starting point at the end. So this means that conditioning x and these two pictures in distribution are the same if you're colorblind. So if I transform every green stuff here into red, you have exactly the same picture in distribution as the one on the left. So if you're combinatorially minded, which I'm sure many of you are, you'll immediately say, no, no, no. That first time I tumbled onto that, said that's not possible. There's a parity problem, right? Because in the first picture, somehow the number of paths that go from x to y has to be even, because you have this chain of loops, and each loop can be, gone in, the path could be, you could go one way or the other way somehow. So, some sort of, if you cut through this picture here like that, the number of trajectories that have to go through that half plane, hyperplane will have to be, even, because everything is done by loops. Whereas here, if you cut by a half plane, because you have this additional one trajectory, it's odd. So you sort of see there's a bit of a contradiction, and that's exactly this miracle result that says, well, it doesn't in the continuum, because you're on the cable graphs, Brownian motion oscillates, so you have this infinitely many, you go back and forth infinitely many times along these edges, so these even odd things are washed out in the continuum, and it turns out that these two things are exactly the same. So the way I like to think about this type of result is saying, you have this web of loops in 3 dimensions around you, and this cable graph around you, and you say x and y are connected. Well, exactly the effect of that is exactly as if x picks up the phone, talks to y via this green line, and the rest of the system doesn't see anything. So you have some sort of independence going on. And okay. So that's one, feature. Now, a second result that I want to mention, which is in the same paper, loops. So that's also 2025, which is the following. Imagine you are in 3 dimensions, but this works in any dimension, in any cable graph, in fact. So now, instead of looking at connectivities, you're looking at topological features of your clusters. So in particular, imagine that you have 3 dimensions, so that's easier to explain. You have one straight line somewhere that you choose in such a way that it doesn't hit the cable graph, right? So it's in sort of the dual graph or something, some straight line somewhere. And imagine that you discover a cluster that contains, so it's a cluster of loops that winds, that contains a non-trivial cycle around delta, around this line delta. Okay? So imagine you have one line here, and then you're observing that one of these connected components actually, contains a whole cycle around this. So this cycle has been created by a union of loops, of individual Brownian loops. So there, maybe there was no loop that itself did wind around delta, but that it's a chain of small loops that creates this cycle in the union of loops. Now, these loops are, not oriented, they don't have a starting point, but there's one quantity you can associate to each loop is whether its index around this line is even or odd. That does not depend on the orientation of the loop. And therefore, you can sum over all the Brownian loops in your cluster. You sum these indexes, and you ask, is this even or odd? Right? Is that clear? So for instance, if you only have one loop that goes around once and otherwise only small loops, the index will be 1, it will be odd. If you have no loop that goes around it by itself, but the chain, or this cycle is created only by a chain of loops, then the index is 0, it's even. Now, you ask the question, I observe the cluster, conditionally on this cluster, what is the conditional probability that this total index is even or odd? And the answer is, so total index of C, or of loops in C, C is a cluster, is even if I condition on C, this is always 1/2. So that means that this, this switching property has the effect, but again, it's only in the continuum, that as soon as you see a cluster, the probability that the total index is even is always 1/2. So there's a magic bijection, if you want, between the configurations that create C with even windings and the one that creates C with odd windings. And again, this is something that's really continuum. But the main story, so just to illustrate this means the following. It has a very strange consequence. For instance, sort of a consequence is that if you observe a cluster that is very, very skinny, abnormally skinny, right? So a cluster which has one very thin cycle in a very fine mesh, delta ZD, right? Then you sort of see that there are only 2 options. With, the other options have a very, very much smaller probability. One option is this cycle has been created by one Brownian motion that went all around. That's it. It's very difficult, very unlikely, but that's one option to construct a cycle which is very skinny like that. And the other option is no Brownian motion went around, and the cycle has been created only by, chains of very small loops that happen to be attached to each other and go around like this. The previous answer tells me that as soon as I observe a cluster, the total index is even or odd with probability 1/2. So if you discard, having more than 2 going around this thing more than twice, the index is 1 or 0, meaning that the conditional probability that actually this loop that you see in the cluster is actually a real Brownian loop that went around and maybe created some magnetic something around the axis is 1/2. And the probability that it's just created by microscopic loops that have been glued to each other and created this big loop is 1/2 as well, but those don't create things. Okay? And there's no way to, if you just observe the cluster, there's no way to know which of the 2 worlds we are in. So you have this thing that in some sense, and so that's led to this paper that we're finishing with Titus Lupu, that in any dimension greater than 7, if you look at your clusters and you look at just the collection of cycles that happen to be part of a cluster, there will be 2 sorts of cycles, just the Brownian loops themselves. The big Brownian loops will be part of a cluster that contains a big cycle, the cycle being the Brownian loop itself. And you have these other ones, which are long cycles created by very small loops. These 2 collections of clusters of cycles have the same distribution in the limit. That means that in the continuum world in 7 dimensions and larger, you have the Brownian loops, the big ones, the real one, and you have some ghost loops, which are just created by agglomeration of small chain of loops that happen to create bigger ones. Okay, now of course this is sort of also reminiscent of some of these things having to do with continuum, what is it that we can observe, right? Of course in physics, the usual way we like to think of physics, or maybe the physicists like to think of physics, is that what is real is what you can observe, right? And what you can observe in physics is not the loop. You can observe, something having to do whether you are at one point, right? And it's like what they're called an observable. It lives at one point, and you see, did a loop go through here? Or you take 2 points and say, are these 2 points part of the same loop, or more precisely in that case, are they part of the same cluster? These are things you can observe and in some sense measure by experiment, by looking at the correlation between things you observe. And here what you see is that this collection of stuff you can observe, in that case you can observe the clusters because these particles are indistinguishable. And how these clusters have been created from the microscopic point of view has some randomness, intrinsic, quantization, if you want, in it, which is, 1/2 of the things are real stuff and 1/2 of the things are fake stuff. So in particular, if you put a little hole somewhere and you see, a cluster went through a tiny hole, did a particle go through that hole or not? You don't know. Nobody will be able to know. The probability is 1/2. Okay, so this is sort of this type of things that you stumble in by looking at these limits of cable graph stuff. And now I want to mention, even more recent results, which is here. So Kai and Ding, which is last week on Archive. Okay. And this has to do with what happens, what is the relation between these cable graph loop soups. So you see, in some sense here, what I'm interested is looking at continuum world with a lattice mesh, which is very, very small, but not 0. You let it go to 0, but there is still this, granular thing having to do that you're looking at what happens on the cable graph. And of course you might say, well, the one natural thing you can try to look at is say, let's try to do the same thing directly in the continuum. So there's a Brownian loop soup, a collection of Brownian loops in the 3-dimensional world that's what we did with Greg Lawler, the Brownian loop soup in 3 dimensions. 3-dimensional Brownian motion intersect, or can intersect, so you can look at, as soon as 2 Brownian motion intersect in 3 dimensions, you can look at the clusters. And then you can ask the same question, which has to do with, what can you say about these, again, you will have indistinguishability features, like of that type that I, wrote in a paper some years ago. And you can ask the question, does the same thing hold in the continuum? And the answer is no. Namely, that the limits of the cable graph clusters, when the mesh size goes to 0, is strictly bigger than the clusters of 3D Brownian loops in the continuum. So that means that what I thought initially was very exciting and going on in dimension 5 actually already happens in dimension 3. Namely, that in the continuum, the story is the following. You have clusters of Brownian loops that are the macroscopic clusters. They are the scaling limits of the big loops on the cable graph. On the other hand, in the scaling limit of the big loops, you are not using any information about the tiny small ones that live in edge inside a given edge, for instance. In the scaling limit, they disappear. You don't see them anymore. And so what happens is that for this structure in 3-dimensional space, if you want to make sense of it, what you have is an overlay of 2 things. The first one is the scaling limit of the big loops. They are important in 3 dimensions. And on top of it, you have some sort of scaling limit of critical percolation in 3 dimensions. On top of it, that comes from the microscopic stuff that agglomerates. And you inject this into your space, and this overlay of these 2 things is going to glue together clusters of 3-dimensional loops. So, a Brownian motion meets another Brownian motion, which is another Brownian motion. You have the cluster. Another Brownian motion is part of another cluster, but these 2 clusters actually could touch and then be glued by this infinitesimal glue that is going to create these limiting clusters of dimension 5½ in the 3-dimensional world, which are the scaling limit of the loops of the clusters on the cable graph. Again, these limits of the clusters of the cable graph are not the scaling limit of the clusters on the discrete lattice, because you are missing these small connectors that live on the edges, for instance, which turn out to be important in the limit. It's not the Brownian one. It's sort of, you have to start with this hybrid model and go to the limit there, and there basically you have this strange overlay. And of course it's very nice because you have this combination between macroscopical objects and sort of these infinitesimal observation of what happens to live inside at microscopic level. And so the real world loop soup, if you want, clusters that you want to relate to these Gaussian free field and so on in the continuum world, has 2 layers of randomness. The macroscopic one, the big loops that you observe, and the small stuff that comes from this granular feature of the model you're looking at, that is actually also providing randomness at large scale. Okay, so these were the 3 stories I just wanted to tell you about. Of course, this is related to a number of other things, and I took some shortcuts. So in particular, in 2 dimensions, which is the one we started with and where the whole thing started, In two-dimension, we know everything. We knew everything before with these clusters of loops in the two-dimensional space, and you have conforming variants and so on. But in two-dimension, it's exactly the case where this microscopic randomness, goes away, which in some sense is natural because, if it's more difficult in two dimensions to have two trajectories to avoid each other than in three dimensions, and so clusters in 3D could have complicated things. Right. So of course this is like ongoing stuff and evolving as we speak. But I thought that was an entertaining story to tell in that context, and it sort of also gives a general perspective of how I try to approach these probabilistic models in general. Thank you very much.
Ladies and gentlemen, it's my pleasure and it's also my duty to transfer now the diploma of the Hungarian Academy of Sciences, which is going to be the evidence that you were elected as a honorary member to the Hungarian Academy of Sciences this year during the annual assembly of the Academy. So let me open this container and let's have a look at the diploma, which is in fact written in two languages, in English and in Hungarian, so you can check if the two sides coincide. Okay, so let's get closer to the audience because we cannot see